AP Cactus AB, Unit 10, Day 5 lesson. So we're going to talk about solids of revolution. And let's see. Let's just start with the problem and kind of attack it with cross sections like we have. Find the volume of solid determined when the region y equals x squared. So that's parabola. Y equals x squared. The x-axis and x equals 2. So this is like 2. X-axis, so this is a region, okay, is rotated about the x-axis. So what I'm going to do is I'm going to sketch the other part of it just to kind of get a visual on it. And then you can kind of see it's going to be kind of circular in nature. It's kind of like a Hershey's Kiss or something, like on its side. But what we could do is we could draw one slice. We'll go ahead and make it vertical. And all the slices are gonna look like these circles, thin circles. So we could take the approach of volume by cross-section that we've been doing. This is a little different. I'm building it off the base, but the cross-sections are circular. And so if we were to just draw one of them, they have a thickness to them, which in this case is going to be dx. They have an area to them, and it's a circle, so it's going to be pi r squared. So we can say, all right, well, the volume is going to be some function of x, dx, and it's going to be circles. So it's going to be pi r squared dx. Now, the limits in this case are going to be 0 to 2. The radius, we can move the pi out in front. The radius right here, the radius is actually the y value. So it's just going to be y squared. But then we want to get it in terms of, so the radius equals y, right? This right here, the radius equals y. But we need it in terms of x. So in this case, y equals x squared. So we're going to plug x squared in for the y. There's still another squared. And so we get pi 0 to 2 of x to the 4th dx. And so now we can go ahead and integrate this. The antiderivative is going to be x to the 5th over 5, 0 to 2. So it's going to be pi times 2 to the 5th, so 2/3 is 8, 1632 over 5. So our final answer is going to be 32 pi over 5. And that is the volume. So we could take the approach of treating these just like volume by cross-section. They're a little different. Not building off of a base or spinning it around. But really, anytime we're dealing with these special shapes where you take a region and you spin around, you're going to get these circles. So we don't need to, we can just jump right into the circle approach. Now, there's two ways we could do these. The first way that we're going to focus on tonight's homework, but I'm going to show you the other way, but we'll kind of start with this one. So there's two approaches. One is you could take it and slice it. If you slice it across the axis of rotation, so perpendicular to the axis of rotation, you're going to get this stack of short cylinders. And it's always going to be pi r squared times the thickness. So they all have a radius, they all have a thickness, and the thickness is going to be dx or dy, depending on the orientation of the slices. The last example we did was dx, so dx or dy will be the thickness of the slices. And so we'll just take that approach, kind of like what we just did. Now, it is possible sometimes that you'll have a hole in the middle. So a disc approach, I'm gonna say it's like this approach right here. I'm gonna call the disc method. But there's a washer because sometimes there's a hole in the middle. And really, a washer is just a disc, bigger disc minus a smaller disc from inside of it. So you have a big R and you have a little r. And so it's really a big disc minus a small disc. So that is a possible situation we're going to run into. Now, there are ways of sort of combining these big and small discs into the same integral, because they're usually going to have the same limits. They both have pi. They both have the same thickness. But you can't do it like this. You can't just say big R minus little r squared. It's got to be big R squared minus little r squared separate. You can't. Algebra doesn't work this way. You can't distribute exponents in. Okay, so it's up to you if you want to do them together. I kind of like doing them separate just to keep things straight. I don't think there's a huge advantage to combining them together. I think there's more danger to it. Now, the other approach, which I'm going to start to show you, is called, I like to call it like the shell approach or tree rings. So think about if you cut a tree down and you can count the rings of growth, and will tell you how many years old the tree was, right? Because I think each ring of discoloration is formed by, the seasons going through a year, and you kind of get this different coloration at different seasons. So you see these distinct rings in a tree trunk. But you can imagine maybe one way of finding the volume of the tree trunk is to find the volume of each tree ring that's nested within itself and then add them all up. So you could think of like a toilet paper roll or something like that too. It has lots of very thin layers of paper that form the full volume. So what we do is we kind of look at the same round object, but like imagine that there's these thin shells. You might even think kind of like a pipe, like they got a thickness. And so there's lots of them. We're going to focus on one of them, but they all fit right inside of each other. Okay. So if we focus on one, we say, well, how do you find the volume of one of these? And this is interesting. Let's see if I can show this on this paper here. So you can imagine one shell is like this. This is one shell, right? One thin shell. And if you want to find the volume of it, it's very thin, but here's an interesting thing. We cut the shell open, and what you get is you get a big rectangle, right? So we had a shell that was circular, we cut it open, and now we have a big rectangle. And so if you cut a shell open, you get this flat rectangular thing, and then the thickness of it is the thickness of the original shell. So the thickness, that's going to be your dx or your dy. The thickness, that's going to be dx or dy. The other dimension, you're going to multiply times the thickness to get the volume. Now, it's a rectangle, so it's it's base times height, right? And the height of the rectangle is the height of the shell, original one. The base, though, is the area is the length all around it before we cut it open. It was this circular thing, right? It's this circular thing, and then we cut it open, and this length all along here, that's the base, and that came from the circumference of the shell. So this equals the circumference, which is 2 pi r. So if we want to find that, we're going to do 2 pi r times h, 2 pi r times h times the thickness, dx or dy. I wouldn't memorize these formulas because you'll get them wrong very easily and quickly, and you'll put a lot of effort into it. Always just imagine how we got these things. Hold a piece of paper up and fold it into a tube and think about where the dimensions come from. And then it shouldn't be too hard, okay, to at least set up the right formula. Okay, don't memorize these formulas. It'll be very obvious very quickly that you don't. That's the technique you're taking and I'll take off a lot of points on tests if it doesn't seem like you actually understand it. And you'll make a lot of mistakes that way too. So let's try a couple different problems that kind of seem like each other, but have very small differences. And we'll talk about how to do it. So first, we're going to take y equals x squared and y equals x plus 2. We need to find the intersections of these curves, okay? And they're going to be the same for all these problems right here. So we could say, okay, well, this is 0, comma 2. This is 0, comma 0. If you plug 0 in here, you get 2. If you plug out, where do these two intersect each other? So we could set the two equations equal to each other. Move everything to one side, equals 0. Factor it. And so then we get x equals 2 and negative 1. So this must be the 2, 2 comma 4. Both of them get the same time. The other one's over here. This is negative 1. We don't really care about that one because we're just focused on this piece right here. Now, on this problem, for part A, we're going to do about the x-axis, and part B, we're going to do about the y-axis. And so that's going to change, that's actually going to change the shape, what it looks like, and the volume it has. But let's focus on, let's try it around the x-axis. So I usually like to label it, make sure I do it right, because sometimes you guys are going to spin it the wrong way. And the next thing I do is I try and graph these dots, all the corners first, and then I connect them. I find it to be a lot easier if I can nail down the corners first to get kind of a reflection of it. Now, if you want to get the disc method or the washer method, you want to slice perpendicular to the axis of rotation. Okay, so this is the axis of rotation. You want to cut into it. If you do that, you can draw these kind of like circles. You're going to get the disc method or the washer method, which is a big disc minus a small disc. So we're going to do everything. If you have vertical slices, we're doing everything in terms of x, dx. The slices are vertical, and the method in this case is the washer method. So we have one slice drawn, which is going to help us a lot. The volume of that slice, don't memorize this. Think of what would the volume of a very thin, short cylinder be? It'd be pi r squared dx. That's the big one. And then there's this small one that we get to subtract, minus pi little r squared dx. I like to use big R for the big one. Now this is your big R, and this is your little r. You always want to label your dimensions on the original area. This down here is just to help you kind of visualize it. Never put it down here. Now, we're going to integrate these. I'm going to just put the pi, squeeze the pi outside. We're integrating left to right. So it's going to be 0 to 2, 0 to 2. Now, the way we find these dimensions is the way we've been finding the lengths of slices since the last chapter. This is a vertical length, y top minus y bottom. This is also a vertical length, y top minus y bottom. Now, the y top and y bottom are different for these, but it's vertical. Now, this big radius right here really is just, if y bottom is 0, then y top, it's just y top. So what is this y variable in terms of x? It's x plus 2. So the big radius at any point along here, the big radius is from the axis of rotation to this outer edge, which is that line. That's always the big radius. Okay. The little one is this length right here. And so y top is actually right here along this curve, which was x squared. So that's your setup. And you could put that in your calculator. I mean, we could clean it up, of course. If we were going to do it by hand, we would probably want to FOIL this guy out, and it'd be x squared plus 4x plus 4. And I mean, we could combine these. They both have 0 to 2. They both have pi's, or you could just keep them separate. if you're worried about messing it up. So the antiderivative here is going to be x cubed over 3 plus 4x squared over 2 plus 4x, 0 to 2, minus pi, x to the 5th over 5, 0 to 2. If we plug 2 in, we get 8 thirds plus 8 plus 8. Put 0 in there, so we get 0 plus 0 plus 0. Minus pi, if you plug 2 in, you get 32 fifths minus 0 fifths. So those will all drop out. So we have what, 16. We could give this the least common denominator. 48, 56 pi over 3. That's the volume of the whole disk without the hole in the middle, and then we're subtracting this whole out. 32 fifths pi. If we want to give these guys least common denominators, it's going to be 15. So this is going to be 280 minus 96, which is going to give you 184? 184 pi. So that's your volume. Of course, we could use a calculator also at some point. But that's the way the work looks. Now let's attack the same problem. Part A, rotated about the x-axis. So this picture looks the same. We don't need to redo. We have all the coordinates of the points and stuff. It looks the same. We're still going to want to draw the reflection of it. So I'm going to redo this problem. We should get the same answer, but this time I want to use the shell approach. Now, anytime you want to use the shell approach, I guess we should emphasize this. You want to slice parallel to the axis of rotation. You want the slices to be in line with the axis of rotation. So this is the axis of rotation. So if we're going to do shells, we're going to slice it parallel to it. So that's one thin shell, okay? Now, something happens here. The shells change. What determines their dimensions change. So we're going to have to do two different sets of shells, okay? The thickness is going to be dy, okay? The slices are going to be shells. So we're going to need to get everything in terms of y, but let's just start with one of the shells. So the volume of a shell, remember, if you take the shell and you slice it open, you get a rectangle. And the base of the rectangle comes from the circumference of the original shell. So it's going to be 2 pi r times the height dy. Okay? And then we could integrate it. Now, we're going to have to go 0 to 2, 0 to 2, and then 2 to 4 separately. So we're going to have to do another 2 pi r h dy, 2 to 4. Now, this is potentially the most confusing part. How do we find these dimensions? Okay? How do we find these dimensions? So the radius of the shell is this. This is the radius of the shell. And the radius of the shell is y top minus y bottom for both of these, but this is what's happening right here. It is not connected to the curves. Is it this curve, this curve, this curve? It's not connected to curves. What we're doing is we're gradually we're starting the radius at 0, and we're gradually making the radius a little bigger, a little bigger, a little bigger, a little bigger the whole time. Really, it's just whatever the y coordinate is so far. So the radius of shells is always going to be x or y. And it's tied to what we're gradually changing the value of. Okay, the height belongs to the curves. So the radius is always just x or just y, depending on the orientation of the slicing. Okay, the h is tied to the curves. Okay, so The h is what's changing as the curves change. So here's the h and here's the h. Now, in this case right here, h is x right minus x left. So x right minus x left in terms of y. So this is going to be square root of y, and x left is just 0 in this case. Okay. When we get up here to 2 to 4, the radius is still y, but the height right here, x right minus x left, x right's along this curve, that's the square root of y in terms of y, and x left is over here, which is going to be y minus 2. And we're subtracting it, so it's minus parentheses y minus 2. So that's the setup. We could clean it up a little bit. I mean, you could totally enter it into your calculator this way, but we could, if we could either clean it up before entering the calculator just to make it a little easier to type, or if you're going to do it by hand. So in this case here, we would distribute this. So it'd be y 3/2 minus y squared plus 2y. So that's a little cleaner. And then if we were to do it by hand, I'm not going to finish the work, but I'll just start it. You would go y to the 5/2, bump it up 1, divide by the new exponent. Y to the 5/2, bump it up 1, divide by the new exponent, minus y cubed over 3, plus 2y squared over 2. I don't know why I put that. So, and then you would keep going. You'd plug it in, or you could do it on your calculator. But if you finish this work out, guess what? You should get 184 pi over 15. You should get the same answer we got above, because it's the same shape. It has the same volume. We're just slicing it differently. Okay. Now, over here, we're going to rotate around the y-axis. We're going to take the same functions, the same region, okay, all the same values, same function, same region. But instead of spinning around the x-axis, we're going to spin around the y-axis. So when we draw the other half, we want to transfer these corners. And now, see over here, it was kind of like this empty bowl with very straight outer edges and kind of a circular inside. And now it also kind of looks like a bowl, but it's very round on the outside. So this shape is different than this shape. We got it by rotating the same region, but in a different way, it creates a different shape. So this is what we're working with. Now, if we want to do it with respect to x with vertical slices, okay, thickness is dx. This time we're slicing. If we slice it vertical, we're getting shells, right? If you slice it parallel to the axis rotation, you're going to get these shells, okay? So we're getting, the slices are vertical, and we're getting shells. You don't memorize it's not going to just be shells every time it's x. It's nothing to memorize here. You got to draw the picture. You got to understand what you're looking at. So if we wanted to try and find that, remember this shell is this like tube, and if you open it up, it's a big rectangle, and the dimension across the top of the rectangle is the circumference of the original. It's this length around here. If we slice it open, it looks like this, right? And so 2 pi r is this dimension, and height is this dimension. 2 pi r h, thickness is dx. Don't memorize that. Think it through real quick every time. You'll be way more effective. Now, the dimensions are in the x direction, 0 to 2. And this time we don't have to do two different sets of shells because this is the radius. Remember, everything should always be based off this original region. Don't work over here. This is just for looks. The radius is x right minus x left, but really it's just going to be whatever the x coordinate is at that slice. We're just gradually making the slices bigger and bigger and bigger. So the x is just, the radius is just x. The height is where the curve functions come in. Y top minus y bottom. Y top is, in terms of x plus 2. Y bottom is the parabola x squared. So that's your setup. You could put it in your calculator like that, or if you're going to do it by hand, you definitely want to distribute this in here. So it's going to be x squared plus 2x minus x cubed. The antiderivative is going to be x cubed over 3 plus 2x squared over 2 minus x to the fourth over 4, 0 to 2. So we're going to get 8 thirds plus 4 minus 16 fours 4. Plug 0 in, 0 plus 0 minus 0. All goes away. These cancel each other out. And we get 16 pi over 3. 16 pi over 3. Okay. Now if we take the same shape, rotate it around the y-axis, same shape, same intersections. Copy all this down again real quick. And then if I want to get a good sketch, I'm going to try and transfer this corner. I'm like, well, it's about that far. And connect the corners, get a good drawing that way. This is the original region that we're focusing on now. Okay, yeah, we get this circular shape. Now, by the way, we got a very different answer. This method and this method. Okay. This should give us the same answer as the one above. It's the same shape. But this time, we're going to slice it dy. And it's going to be perpendicular to the axis of rotation. So you're going to get these disc washer shapes. Now, it's a little inconvenient this time because look, if you slice it down here, you get a different disc washer. So we're going to have to integrate 0 to 2 a certain way and then 2 to 4 a different way. The dimensions are different. So now we're not memorizing this. Remember, well, what's the volume of a short cylinder? It's pi r squared times the thickness, the height, which in this case will be dy. And so from 0 to 2, we're going to use that approach. But then, and there's no, but from 2 to 4, pi r squared dy is going to be a little different. And then we're going to have a small radius that we have to subtract from it. Pi little r squared dy from 2 to 4. So that's our approach. Now, at first, the big radius, for disc washers, for shells, radius is just x, y, but for disc washers, the radius is where it gets complicated. It's x right minus x left. It's just going to be, it's going to be where this x coordinate is, but we need it in terms of y. So x equals positive square root of y. So it's going to be square root of y. 2 to 4, the big radius right here, it's the same thing. It's x right minus x left. It's this dimension here that we're not doing these, we're not subtracting these. Okay, I got to find the big radius, little radius separate. So it is, again, just the positive square root of y. But then the little radius from 2 to 4 is this guy right here. And it's this x right minus this x left. And it's the x right here. It's going to be y minus 2. So that's your full-blown setup. And even if you're going to type it in your calculator, it would probably be worth it to go ahead and simplify it a little bit. All right, square root of y squared is just y. This, you'd FOIL it, y squared minus 4y plus 4. So that's a little simpler. And then if you're going to do it by hand, then you would go with this. It's going to be y squared over 2. And it's going to be y squared over 2. And it's going to be y cubed over 3 minus 4y squared over 2 plus 4y. It looks very different than what the work that we did right above, but this should give us 16 pi over 3 again. So this is going to be 2 pi, right? This is going to be 16 over 2 is 8, minus 2 squared 4 over 2 is 2. Put 4 into here, we get 64 thirds, minus 32, plus 16, minus 8 thirds, minus 8, plus 8. Those guys cancel each other out. So we have 8 pi from these two, minus, this is going to be negative 16. And we have 64 thirds minus 8 thirds would be 56 thirds. Minus 16 would be 48 thirds. So that's going to be 8 thirds minus 8 thirds pi. Oh. So 24, it's going to be 16 pi over 3. Same answer that we got up above. So these are definitely going to take some getting used to. Pictures are huge. There's no way you're pulling this off without a picture. And really understanding what you're looking at. If you try and memorize formulas for this, it will go horribly wrong. It won't even be worth it. You'll do it. It won't even make any sense. I'm telling you. There's two different situations. Understand them. Be able to kind of see the simpleness of them, and use what you've known from geometry before. Now, in tonight's homework, just to clarify, it says that you're going to be using dx and dy, but I don't want it to be dx and dy. I want it to be or. I want us to just use the disk washer method for today, okay? Because the shell method is its own thing. Let's just practice one approach at a time and get the hang of it. Okay, so I'll help you out right now, like on the homework. Let's take a look at it. Now, on my solutions, I'll have the dx and the dy that both give the same answer. But here's the deal. All I want you to do is set them up. Extra credit for evaluating them by hand. I would probably evaluate all of them with a calculator. Just get used to it. Extra credit if you do it by hand. Okay? Check it with your calculator, though. I'm focusing on setup. That's the hard, new, challenging part. Yeah, integrating and getting all the numbers and details right is challenging, but you've had a lot of practice with it. You just got to, but that's not a new thing. So read the problem. Find the volume. Y equals x squared. Okay. 0 to 4. You've already been given the intersection. Okay. We're going to rotate it about the x-axis. Okay. Make sure you rotate it in the right way. So the first thing I'm going to do, I'm going to draw the other half. Okay. Now, we want to do disk washer method, which is always perpendicular to the axis of rotation. Your slices are perpendicular to the axis of rotation. Okay. Sometimes that's going to be dx, sometimes it's going to be dy. So draw one slice perpendicular to the axis of rotation and draw. Okay, so this is going to be a disk method, and it's going to be dx. Okay, next one. If we revolve it around the y-axis, I'm going to draw my other half over here. Start with the corners. If I want to get disk washers and avoid shells for now, disk washers, thin, short cylinders, I want to slice perpendicular to the axis of rotation. Draw one slice. Okay, now remember that all your dimensions need to be determined off the original region. Okay, limits, dimensions. Okay, this one's going to be dy. Everything's going to have to be y. Okay, this one right here, rotating it. This one's kind of crazy. Or not crazy, but interesting. If we want it to be disk washer method, we want to slice perpendicular to the axis of rotation. Okay. Now, by the way, this looks like a sphere, so you should be able to check your answer by using the formula for a sphere. That's not the way you're going to get credit, but it should come out the same. It's kind of an interesting way to find a sphere. Okay, next one here. This is the region, and I'm going to spin around the x-axis. So we want to try and get the corners, something like that. Okay. If you want dishwashers, you want to slice it perpendicular to the axis of rotation to get your one slice. Okay. This one here, now things start to get a little more interesting here because the axis of rotation isn't on the x or y axis, but it's got to be vertical or horizontal. I'm not going to do any slanted axis rotation. I get weird. So we want to draw one slice. If we want it to be dishwashers, it's going to be perpendicular to the axis of rotation. Okay. You got to be careful when you're finding the radius now. The radius, this is the right side of, this is your little radius. And this is your big radius. So this axis of rotation, which is often 0 on all the other problems we've done, now has a value. So this big radius is going to be pi minus what are the x coordinates here. The little radius is going to be pi minus whatever the little x coordinate is here. In terms of y, that's going to be a y problem. 6, same kind of deal. We have a shifted axis of rotation. Okay, and then if you want dishwashers, you're going to slice perpendicular to the axis of rotation. Okay, now remember, always get your dimensions and everything off of the original region. This up here shouldn't be where you set anything up. This is just to help you kind of visualize and draw slices. So there's a bunch of help. Just do it the one way for each problem. You don't have to do any shells today. Okay, that's it.